Okay, well, this is the solution to test number 1, which hopefully you've gotten back by now. So I'm just getting out my calculator here. Okay, so problem number 1 was the square root of x squared plus 1 y prime minus xy equals x, with the initial condition y of 2 equals 5. Okay, so in these separation of variable problems, first thing you have to do is replace y prime with dy over dx. And then you can multiply everything by dx to get that dx out of the denominator. So you'll have square root of y squared plus 1 dy minus x times y times dx is equal to x dx. So both of these get multiplied by dx. Then we'll move everything that involves dx to the right hand side. So we'll have as xy plus x times dx. And luckily for us, we have this common term in the stuff on the right hand side. So you can factor out the x. That leaves y plus 1. And the reason I put in this order is because I have x, y, and then the differential part. I could have put the x at the end, and now you can see that we can separate them. So if we divide both sides by y plus 1 and divide both sides by the square root of x squared plus 1, you get that. So that's our separation issue. Now we can integrate. So we integrate 1 over y plus 1 dy, and we integrate x divided by the square root of x squared plus 1 dx. So the integral of 1 over y dy is just the natural log of y plus 1. Now, you could say u is equal to y plus 1, so du is equal to dy. So you'd have the integral of 1 over u du, which is the natural log of the absolute value of u. So the integral, if we make those substitutions over here, we get the integral of 1 over u du, because in this case du equals dy. On the right hand side, we'd let u equal x squared plus 1, so du is equal to 2x dx, or x dx equals du divided by 2. So in terms of the u over here, we get 1 over u du, integral of 1 over u du. Here we get 1 over the square root of u times du divided by 2. So the integral of 1 over u du is the natural log of the absolute value of u. The integral over here, well, we have to rewrite this as u to the 1/2, and then you move it to the numerator. So you get, okay, we'll factor out the 2, integral of u to the minus 1/2 du. Okay, so what you end up with is 1/2, add 1 to the exponent, divide by the new exponent, add your arbitrary constant c at that point. You'll notice that this 2 times 1/2 is 1, so that gets rid of all that stuff. And then we can plug u back in. So on the left-hand side, we get the natural log of y plus 1, and on the right-hand side, we get u, which is x squared plus 1 to the 1/2, but that's the same as the square root, so we get the square root of x squared plus 1 plus c. Okay, now because I don't have any coefficient in here except the implied 1, I can use the inverse properties of logarithms and exponents to do that. E to the natural log of y plus 1 is just y plus 1. So we're going to assume y is greater than 0, and that way we can get rid of the absolute value sign. On the left-hand side, or right-hand side, remember we have, this is the same as e to the square root of x squared plus 1 times e to the c. So we have the same base. So you can break this sum of exponents into two separate exponents, and we can say that this e to the c is just another c. So that's the general solution. And then we can use our initial conditions, which said y of 2 equals 5. So this is the y value, and this is the x value. I guess one thing we could also do is solve here. Y equals c e to the square root of x squared plus 1 minus 1. Okay, so y is 5. 5 equals c e to the square root of x squared plus 1 minus 1. So if we add 1 to both sides, we'll get 6. 6 c e to the square root of 5. Therefore, c is equal to 6 divided by e to the square root of 5. That's where I need my calculator. 6 divided by e to the square root of 5. So I get c is equal to 0.641. And therefore my final solution is y is equal to 0.641 e to the square root of x squared plus 1 minus 1. And let's just double check. So we're going to try y of 2 should be equal to 5. So I get 0.641 e to the square root of 5. 2 squared is 4 plus 1 is 5 minus 1. 0.641 times e to the square root of 5 minus 1. And I get 4.997, so approximately 5. So that looks like it's the right answer. So a lot of guys didn't get to this point, and then you got some really crazy integral. So that first problem was worth 30 points. So I don't think I took off. Well, I might have taken 20 off. But you know, if you get to a really crazy integral, then you should realize that I don't give you really crazy integrals. So hopefully you would have gone back and checked it out. Okay, the second problem, you guys did some of the best job that I've seen on this, so that's good. I guess that shows you've got pretty good algebra skills, because that's basically what it is. So we have this original differential equation, which is not separable, and part of that is because you've got this x times y thing, so it's, you can't factor. And I guess the same way here, you got x squared and y squared. So anyway, this is not separable, but it is homogeneous. So the substitutions are y equals this new, or however you want to write it, x, and the differential dy is equal to nu dx plus x d nu. So making those substitutions, so for y I put in nu x, same thing here, nu x squared instead of y squared, then I multiply by nu dx plus x d nu, so that's that part. Then I've got minus x squared plus y squared, so that's nu x again, squared close parenthesis times dx. So that's the original substitution. Okay, so the next one, I'm going to multiply these things out before I try to use FOIL. So I'll get nu times x, so that's x squared nu. Here I square both of them, so I've got x squared nu squared, and that's multiplied by nu dx plus x d nu minus x squared plus x squared nu squared whole thing times dx equals 0. So this e square nu, e square x squared nu squared, I switch the difference, I switch the order. Okay, now we'll use FOIL. So this is the tricky part. So first is I've got x squared nu dx. So that gives me x squared nu squared dx. Okay, so that's first. Let's do next, plus outer. So that's these two. So I've got nu x squared nu times x. So that's x cubed nu and then d nu. So I've got x cubed nu d nu. Then I've got enter. So that's these two. So I've got x squared nu cubed dx. X squared nu cubed dx. And I've got L. So I've got these two. So I've got x squared times x, nu squared, x cubed nu squared d nu. So two of these should have dx, two should have d nu. And then I've got this, so I've got negative x squared dx, and then I've got negative x squared nu squared dx, and that all equals 0. Okay, so everything's multiplied out. Let's see if there's anything, do we have any that are the same? Can we eliminate anything? Well, this one and this one are both x squared nu squared dx. This one's plus, this is minus, so those cancel out. And then I can divide everything by x squared, because all of these have at least x squared. So divide by x squared. So this one becomes x nu d nu. This one becomes nu cubed dx. This one becomes x nu squared d nu. And then we got one more, which just becomes minus dx. And that equals 0. So we'll move all the stuff involving dx to one side. So you get x nu d nu stays on the left-hand side, plus x nu squared d nu. And then we got dx. This becomes positive, and this one becomes negative. Okay, so here we can factor out the x in the front. And what we have left is nu plus nu squared. And then we'll factor out the d nu on the other side. So this goes to the right, this goes to the left. What's left is nu plus nu squared. And back here we can factor out the dx. So we get negative 1 minus nu cubed dx. And then finally, let's put all the new stuff on the one side. So you'll have nu plus nu squared d nu. So that's what's on the left-hand side, and then I'll divide by 1 minus nu cubed. And on the right-hand side, I've got dx, and I divide everything by x. And that's your answer. Obviously, this one would be easy to integrate. This one, what would we do? Probably we'd break it up into two parts. Nu squared over 1 minus nu cubed. You could that would be something to do with the natural log of 1 minus nu cubed. And nu over 1 minus nu cubed, you probably have to use trig substitution on that, which we haven't talked about yet. So that's one reason you can't solve these problems. Okay, so that is number 2. The next one, yeah, everybody did pretty good on this one. Just made some silly errors. So let's call P population. Population 0, 40. Population at 42 equals 900. And L, carrying capacity, is 1500. So it can never, this number can never go greater than 1500, so that makes sense. So you got P as a function of T is L divided by 1 plus B e to the minus K T. So the first thing we do, and I think everybody got this right, was to solve for B, because we know what L is. And you do that, you solve for B using the initial condition. So what we'd say is 40 is equal to 1500 divided by 1 plus B e to the 0 power. Because if you stick 0 in here, it doesn't matter what K is. And remember, e to the 0 is 1, so you get 1 plus B. And then you get to flip these around. So 1 plus B equals 1500 divided by 40, which is 1500 divided by 40. And something doesn't seem right. What did I do wrong here? Oh, that's because that is not the carrying capacity. It's like something's wrong. Okay. Carrying capacity is 3,000. Okay, just need to read the problem correctly. 3,000. 3,000. Okay, this makes more sense. Okay, 3,000 divided by 40 is 75. And then subtract 1 from both sides, you get B equals 74. Okay, so right now what we know is that the population as a function of time is 3,000 divided by 1 plus 74 e to the minus kt. So now we're going to use that one data point, P of 42 equals 900, to solve for K. So this is my X value, this is my Y value. So you get 900 is equal to 3,000 divided by 1 plus 74 e to the minus K times T, which is 42 years. Again, we can switch these out. Changing negative K times 42 to negative 42K. And then on the right-hand side, you have 3,000 divided by 900. And so what is 3,000 divided by 900? 3.33. Okay. So we subtract 1 from both sides. We get 74. E to the minus 47k is equal to 2.33 divide by 74. So first I got to subtract 1, divide by 74, and I get 0.03153. Okay, so now we take the natural log of both sides. So e to natural log of e to that is just negative 47k, and the natural log of that is negative 3.457, and divide both sides by negative 47, and I get 0.0735. Let me double check and make sure that's right. Check somebody's answer here. Got the answer right. Okay, that person didn't have it right. So you got, what did I do wrong here? Oh, it's 42. Sorry again. That's why you got to be careful. Okay, it's 42. I guess I saw that. Thought it was a 7. Can't read my own writing. That's always a... Just did I do it wrong again? Yep. Okay, let's try it again. 42. I need to fix that down there. 42. Okay, 42. 42. Okay, now divide by 42. Times 47, divide 42. Okay, so that's the number you guys got, 0.0823. So that's the constant k. So now I have the function fully defined. It's 3,000 carrying capacity over 1 plus 74 e to the minus 0.0823 t. And now I can, now I need to figure out the time to get 1500. So you would say 1500 equals 3000 divided by 1 plus 74 e to the minus 0.0823 t. Solve for t instead of k. Okay, so switch the numerator and the denominators from opposite sides. So you get 3000 divided by 1500, which is 2. Subtract 1 from both sides. You get 2 minus 1 is 1. Then you divide both sides by 74 to get e without any number in front except for 1. So you get 1 over 74, whatever that is. And then you take the natural log. So natural log of 1 over 74. So what is that? Natural log 1/74. So we get negative 4.304. But the natural log of e to that is just the exponent. 0.0823t is equal to negative 4.304. And divide both sides by negative 0.0823, not t, just because that's what we're trying to solve for. And hopefully that's like 57 years. Divided by 0.0823, or 52.3 years. Okay, so I think that's right. Yeah, depending upon how much you round it off. Some people got 53.7 because you rounded off to 0.08 instead of 0.0823. So anyway, it was around 53 years. Okay, the next one most people got as well. So it says the voltage, some function of time. And because it's an exponential decay, it's going to be some initial value v0 e to the minus kt. So it says exponential decays in an exponential fashion. So that's exponential decay. Now you could just say v0 is equal to 10 because it says the initial voltage, or you could say v of t equals 0 equals 10. So you plug that in. 10 is equal to v0 e to the minus k times 0. So this is e to the 0, which is 1. So you just get v0 is equal to 10. Okay. So it's 10 e to the minus kt. By the way, the other two problems were worth 30 points also. This one was worth 20 because it was a lot simpler. Okay, so that was using the initial condition. And then we have that after 4 seconds, the voltage is 2. So this is the Y value, 2, and the T value is 4. So you get 2 equals 10 e to the minus k times 4. So we need to solve for k. So you'll have 2 divided by 10 equals e to the minus 4k. A lot of people thought you had to use the half-life, but half-life only counts if it's radioactive decay, as well as it has to say half-life. So don't just assume that it's a half-life problem. A lot of the typical exponential decays are half-life. Okay, so 2 divided by 10 is 0.2. Take the natural log of both sides. So the right-hand side just becomes negative 4k, and the natural log of 0.2 is negative 1.609. So if you divide both sides by negative 4, you get k is equal to 0.402. So now we know V of t is equal to 10 e to the minus 0.402 t. And then the final one, what would be the voltage after 8 seconds? So that means you're evaluating the function at t equals 8. So that's just plugging in 8 into your expression. So if you take 10 times e to the negative 0.402 times 8, you get 0.401. It's kind of a coincidence. That's 402, that's 401. I don't think there's any significance to that. I think it's just a coincidence. And then finally, the last problem is the first order linear differential equation. So that was worth 30 points as well. So there were a number of different errors here. First one is put it in standard form. So to put it in standard form, you need y prime by itself. So to do that, you need to divide everything by x. So 2 divided by x is 2 divided by x. You still have the y term. Almost forgot that. This divided by x is x squared, and that divided by x is 1. So that's the standard form. So p of x is this part right here. So it's 2 over x. As a consequence, my integrating factor is equal to e to the integral of 2 divided by x dx, the integral of e to the integral of p of x dx. So the integral of, well, what we do is we take the 2 outside. The integral of 1 over x dx is equal to the natural log of the absolute value of x. Now, I think one person forgot to move this inside. So you move that inside the natural log and it becomes the natural log of the absolute value of x squared. But if you square something, it's essentially doing the same thing as taking the absolute value. So you can remove the absolute value at that point. And then the inverse properties of logarithms and exponentials says that the integrating factor is x squared. So we take that integrating factor and we multiply by the equation in standard form, which is right here. So it's y prime plus 2 over x. Y is equal to negative x squared plus 1. So we're just saying multiply the integrating factor by everything. So you get x squared y prime here, and then you can simplify x squared divided by x is x, and the 2 sticks around. So x squared divided by x is x. So you get 2x, y, and on the right hand side we get negative x to the 4th plus x squared. So x squared times x squared is x to the 4th. 1 times x squared is x squared. Now, notice the derivative of x squared equals 2x. So we know it's what it needs to be. So we say we can collapse these two into the u of x times y. And then we put a prime. And that's equal to negative x to the 4th plus x squared. And then one final thing is, remember, this is the derivative of x squared y with respect to x. So I can then multiply both sides by dx. So I'm left with this differential. The differential of x squared y is equal to negative x to the 4th plus x squared, all times dx. And now I can integrate. So the integral of the differential, and here we have the integral of negative x to the 4th plus x squared, this whole thing times dx. And remember, the integral of dx equals x plus c. The integral of dy is equal to y plus c. So when you have this, when you integrate a differential, we just get whatever that thing we have the differential of. So in our case, the integral of d of x squared dy is equal to x squared y. And then the right hand side we integrate. So we add 1 to the exponent, divide by the new exponent, add 1 to the exponent, divide by the new exponent, add our arbitrary constant c. And then finally, to explicitly solve for y, we divide everything, all the terms by x squared. If you divide this by x squared, it becomes 1. Here we get negative x cubed over 5. X cubed divided by x squared is x, so we get x over 3. And we get our arbitrary constant divided by x squared. So that's our general solution. And then we have our initial condition, y of 1 equals 2. So again, this is the x value. This is the y value. So 2 is equal to negative 1 cubed over 5 plus 1 over 3 plus c over 1 squared. So that's 2 is equal to negative 1/5 plus 1/3 plus c and if we take 1/3 minus, so 1/3 minus 1/5, so we find a common denominator, which would be 15. So you'd have 5/15. 1/3 is 5/15. 1/5 is 3/15. So 5 minus 3 is 2. So we get 2/15. And 2 is 30/15. 2/15 plus c. So if we subtract 2/15 from both sides, we'll get 28/15. So that's c. So the final answer is y is equal to negative x cubed over 5 plus x over 3 plus 28 divided by 15x squared. And there's your answer. So that's it. Like I said, they're all worth 30 points except for the fourth one, which was worth 20 points. And what I did is I looked at the average of all the tests that we had last semester for you guys, for the 9 people taking this class. I think it averaged out to an 82. So the average for this test was an 84, so it was 2 points higher than what your average was last semester. And if you look at the grades, they, they're not that far from what you did last semester. So I think relatively speaking, they're appropriate as far as what you know about the material.